get started. Oh, he has to come. Okay. So, any questions from previous class? So, previously we talked about the ionic bonding, right? So, then we found in the ionic bonds, if you look at the total potential energy, basically, if you look at the repulsive force, you have some, something R ring or something, right? So then in the ionic case, what is that potential energy? It's basically 1 over this 4 pi epsilon 0 R, then we have this, whatever the modeling constant, right, log n2 or something. That's what I asked you to explain what it is. So, because this is the ionic, because you have positive, negative, right? That's the. So this actually the energy you are calculating is basically we call the lattice energy, right? Cohesive energy means lattice energy of the ionic bonds. Because these are all the sodium chloride. Is exclusively electrostatic, right? So it's governed by 1 over R dependence. That's exactly what this homework is about, right? But I'm not going to ask you to calculate this one or anything, just explain that. So let's get started. Then in the covalent bonding, I think these are basic chemistry, right? In the covalent bonding, so these are the strongest bonds, right? Compared to an ionic bond, these are more stronger. But in this case, basically, so ionic bonds happen mostly between atoms, but the final product is mostly non-conducting solids, right? So basically, things like sodium chloride, these are good ionic conductors, but they are not electrical conductors. So please remember that one. Even potassium bromide, or we discussed about another rubidium bromide, right? These are all ionic crystals, but not good electrical conductors. But covalent bonds, they are even stronger than the ionic bonds, but these mostly happen between non-metals. Like ionic bonds mostly metals, right? Sodium is a good metal, but covalent bonds mostly, like carbon is actually, I don't know, is more like the semi-metal. So it's not exactly the metal. So even silicon, if you take silicon, so silicon is a semiconductor, right? It's not a metal. So in general, covalent bonds happen between non-metals. So carbon is something you can argue, right? Carbon is a semi-metal. But the only difference is in this case, if you take the atom, the electrons. So in the ionic case, what happened? This one is giving up electron, another one is gaining the electron. That's how we make ionic bonds, right? In the covalent case, they are basically sharing the electrons, right? So it belongs to both. So that's the difference, right? So in case of carbon, so carbon, what is the atomic number? Everybody remember?
The atomic number?
Yeah, atomic number?
6.
6. That means you have 2 in the K shell, then you have 4 in the outer the L shell, right? So that means you have 4. These are the valence electrons. So if you take 2 of them, basically the electrons from each atom they are sharing, right? This electron belongs here, and also this electron belong here. So that's why you need to eventually it has to get to this something called the normal gas configuration, right? That means how many electrons you need? 8, right? So that's why you need to have carbon atom. If you take the hydrogen, right? It can bound to hydrogen atom from each. Okay. So that this way you are making carbon becomes 8, right? Noble gas configuration. So that's how we make the covalent bond here. So if I had the here we are talking about just the methane gas, right? So everything is, so you can see you are getting 4, 2, 4, 6, 8, right? Same thing can happen even carbon. But in that case, depends, you can have single bond or double bond or even triple bonds, right? That's a interesting. Then depending on that, you will have how many hydrogen you need. So that's what I'm going to show you. Okay. Interesting thing is covalent bonds, basically you are not giving up electron, it's just sharing electron. So that's why they are more strong. So if you think about simple hydrogen atom, so when they covalently bond, just think about two hydrogen atoms far apart each other, right? So hydrogen atom is what? In the nucleus you have only one proton, right? No neutrons. So in the outside you have one electron. So these are independent too. Now if you try to bring them together, what happens? Because these are charges, right? Positive nucleus, negative electron, positive. So we have all this interaction happening, right? So if you think about when you bring them really close, they are now making the covalent bonds. You can think about all these interactions. You can have electron-proton interaction, or attraction, proton-proton repulsion. So all this electron-electron repulsion, all these forces are present there, right? But the way it makes the bonding is, just imagine these two atoms are here. So they are now getting closer. So we can think about one thing, quantum mechanics. We talk about fermions, right? Electrons are fermions. If you think about your wave function of electron, remember we said everything about electron is represented by the wave function, right? So quantum mechanics wave function. So that wave function actually has dependence of spatial parameters as well as spin, right? You see, electron has a spin also. It can be up or down. So that means your wave function can be a function of your the distance, and also I'll say it's a sigma is my spin. Don't worry about that. So this one I can write as maybe something that has only the spatial dependence, and this one has only the spin dependence, right? So one thing everybody should remember is, for electron is a fermion. Fermion means your total wave function should be asymmetric, right? So total wave function should be asymmetric. What is asymmetric means? If I change this one to negative, your answer will become negative, right? Any function, if I have psi x, if it's a function, if it's a symmetric function means, if I change this one to minus x, this becomes same as x, right? This is symmetric. Asymmetric means if I make this one minus x, this becomes minus psi x, right?
So like odd even function?
Exactly, yeah. So this is the even function, this is odd function.
Oh, that makes sense because
Yeah.
the solutions are.
Exactly, yeah. So, but in this case, if you take your the electron as fermion, so now if you so this is the wave function for one hydrogen atom, this is the wave function for other, this is the spatial part, right? The arc dependence. Now, the total should be asymmetric, right? In this case, we can see the spatial part is symmetric, right? Then the spin should be what? Asymmetric, right? Because if you multiply two, symmetry, if you multiply you get symmetry, right? Asymmetry, if you multiply you get still symmetry, right? The asymmetric versus symmetry you get asymmetric, right? It's like positive, this is negative, this is positive, negative, right? So this is positive, you get always asymmetric one, right? Because this is negative, this is positive. Just think about positive and negative. Is that clear? So in this case, you can see these wave functions. For one, it is like this symmetric, other one also symmetric. So then when you add these two, this is how they add up, right? So this is symmetric total wave function. So in that case, you can definitely tell your spin wave function should be asymmetric, right? It has to be asymmetric. So now think about asymmetric wave function. So the first hydrogen atom has symmetry this way, other one is negative. That's asymmetry, right? So negative becomes. So now in this case, we know that your spatial part is asymmetric. That means spin part should be symmetric. Right? Your total should be asymmetric. Spin symmetry means if you change from spin up to this one, symmetry means it's the same. If it is asymmetry, that means your negative term comes in, right? So that's okay. So then, so this is individual one. So when you add this one, now this is a total wave function, right? Psi 1 plus psi 2, psi 1 plus psi 2. Remember the probability now, where you can find the electron. What's the probability density? That is psi times psi star, right? Your probability we discussed about this one. Probability function is basically psi star times psi, or basically psi star, right? Square. So now if you take the probability, what happens? So this one you just square, you get this one, right? Basically square. But here when you take the square, what happens? The negative part also become positive, but this part is 0. You can see at this point, this is 0. But here in the center, you have finite probability of finding the your electron, right? So that's why we have something called, this is we call the bonding configuration, because they really make the bonding, because you can find your the electrons at the center. But here probability is 0. That's we call it anti-bonding situation. So here you can see this is a bonding situation, because they really you have finite probability here, right? But if you look at here, so this is exact same thing I'm proving. What is the probability of finding this one here? 0, right? So we don't see, that's an anti-bonding. Typically we call, these are sigma bonds. We say sigma 1s, other one we call sigma 1s star, right? This is sigma 1s star bond. That's an anti-bonding configuration. So, these some basic things you think we should remember. So then next thing is metallic bonds. So we know metals, if you take copper or silver or gold, these are metals, right? So what holds these in metals atoms together? So what is the property of metals? If you take atom of a metal, these electrons are, we call the free electrons. So these electrons are not really bound to the atom. They are free, can move anywhere. That means quantum mechanically, I can say this electron is here, or you can say it is here. It can be anywhere, right? So same thing, from each atom, these electrons can be anywhere, shared by all the atoms. So that means in the metals, we call this a electron cloud. So these electrons, ideally it comes from this atom, but in metals, it doesn't really belong to this atom. It can be somewhere here, right, anywhere in the metal. So that's why we say in metals, we have something called the electron cloud surrounding the atoms. So that means you have this negatively charged electron cloud, then you have positive ions because you lose this electron, right? These ions are positively charged. Actually, those electron cloud will hold this crystal together. Because if the ions are positive, what should happen? They should repel each other, right? Positive charges should repel. So, but you have this electron cloud intermediate in this metal, they will help you to hold the atoms together in the metals. We can see this, the electron cloud is like a glue to hold these atoms in the metal. So these are also not very strong because not really making like ionic or covalent bonds, right? These are kind of weak bonds. But important thing is, because of this nature, metals become more like they have a more plastic deforming ability, or we call it a ductile material. everybody familiar with the ductility and malleability? Ductility means if you try to use a tensile strain, right, you can really draw that metal. So that's why we can make a fiber kind of thing from metals, right? Malleable means if you compress together, still you can hold them together. That's the reason these metals can be more ductile and more malleable. You can see how these electrons, I had a nice picture, it doesn't work here. These electrons can go anywhere. That's the reason metals are good conductors, right? These electrons can be anywhere. If I apply small potential difference, that will pass the current, right? These electrons, if I put some, because you have these electrons everywhere, charge E, if I apply some potential difference here, this negative electron will push, positive electron will attract, you will have these electrons moving, right? What is that? That's a current. So that's why metals are good to conduct charges. That means moving charge means current, right? So you can have current passing through these things. These are metallic bonds. So then van der Waals bonds. These are some of the most weakest bonds. So these happen especially for molecules, even in atoms. So they are very weak bonds. So the reason of having these bonds is due to something called the natural polarization. Polarization means charges become separated, right? So especially if you take atom, if you have positive, like your nucleus has protons and neutrons, then your electrons are in the orbitals, right? So if you have this spherical configuration, these electrons, these positive charges and these negative charges will be neutralized, right? So but in some atoms, so you can have this, the nucleus can be slightly off from the center. That means you can have kind of, suppose the nucleus positive charge is kind of off center, suppose if I go here, right? So then you have some kind of charge redistribution, positive and negative charges. What is this one? Same charge, right? Q, then this is minus Q. What do you call that? That's a dipole, right? So we have dipole moment P given by that charge times that separation we call T. That's the dipole, always from negative to positive.
Would you ever calculate the torque of that one?
Yeah, if I put this one in electric field,
Yeah.
then it will experience a torque given by
P cross V.
P cross E, right? Or you can have a potential energy given by minus P dot E. That's in electric field. Same thing happens in magnets. In magnets, what happens? You have a spin, right? You can have this spin, we call the magnetic moment. So if I have a P field instead of electric field, they will experience the same thing. So we'll talk about that one later.
Magnet is the current times area, or is it?
Yeah, so if you have any current passing in a circular orbit, you have something called the dipole moment, right? So given by this I times area. So we'll talk about this one later, don't get confused. Right now we only talk about electrical dipoles, not the magnetic dipoles. So, like I said, this is just for atoms. Even if you have a molecule, so that means more than one atom, right? Those molecules also can be polarized. So that's how van der Waals forces are created. If I take like iodine molecule, so this iodine has like two iodine atoms, right? So each one you can actually, no, this is one molecule of iodine. So you can see some charges are moved to one side. It's more like a fluctuation of these charges. So then you have a dipole moment this way, you have dipole moment this way, right? That means all the molecules we have individual dipoles. So this is the same material. We call this a homo nuclear molecules. So homo means it's the same material. But if you have the hetero, that means like hydrogen chloride or something, you can still have polarized molecules. So these are like say hydrogen and chlorine, right? Still they can have this polarization. Here I'm talking about iodine and iodine. Right? There's a homo nuclear, so these are hetero. So now if you have this kind of polarized molecules, so they can form the crystal, right? So that's the way of making the crystal of this polarized molecule is due to the van der Waals forces. That's because if you have two dipoles, they always have some kind of interaction, right? So how does that work? Maybe if you simply, if you know how to calculate the dipole field due to one dipole. Anybody remember if I have a dipole moment like this one, right? That means you have minus q charge, plus q charge, I have a dipole moment, right? If I, at a distance here, anybody remember what is the electric field? This is easy, right? It's typically in this direction, given by this distance is r, your electric field is, the magnitude is given by 1 over 4 pi epsilon 0, that P divided by R, anybody remember? Cube.
Oh yeah.
Because if you have a simple charge, only one charge, that oh no, this is for the electric, yeah, that's the electric field, that's correct, yeah. This is a force, right? So if you have a charge, this electric field is given by Q over 4 pi epsilon 0 times square, right? Yeah, please remember. If you have a dipole, you have 3. Because dipole field is decaying very fast. Because for electric field magnitude with R, if you have a charge, it's going like this, Q over R squared. If you have a dipole, it goes much faster because this is going like Q over R cube. So that is easy because this is at this perpendicular distance, right? But how about if you have at the angle like this R? Still you can calculate this force, right? It's very simple. So I can write that one in general terms. If I have my dipole like this, at the distance here, I can calculate my electric field. Don't forget about any dipole here. So if I have dipole with dipole moment P1 at a distance R, what is my electric field? So you can easily calculate. If you calculate, what you get is 1 over 4 pi epsilon 0, just like before. This is the term we had here, right? P over R cube, negative. Then you have another term because now this is not perpendicular. This is the term you get 3 times, and you must have done this one many times. Yeah, let me write down here. For any general direction, your dipole field is given by this. I can write for the one term is, we know that is P1, yeah, perpendicular, this one, right? Divided by 4 pi epsilon 0 R cube. That's fine, right? But because of that other direction, you get another term that's given by actually 3 times this P1 dot this unit vector of R, because this is the one we are talking about. This is my P1. I want the electric field at this point. This is R. That means your unit vector is R, this one, right? That given by this P1 times this unit R vector in that direction divided by 4 pi epsilon 0 R. You can easily show this one. That's the electric field due to this dipole. Is that clear? So that's basically the 1 over 4 pi epsilon 0 r cube I take out. These two. Now think about, this is one dipole, due to that pole I have electric field here. Now I have a second dipole at this place. What is the energy of that one? You already asked me, right? That's P dot E. Right?
Oh, yeah.
So due to this one, now I have electric field here, that I know about that one. Now if I have a second dipole here, the energy would be P2 dot that E, right? So that I can easily write, because now also we know P2, you can calculate, actually we should not take, yeah, please think this way. This dipole is not independent. This is actually induced by this dipole field, because I have some molecule here. So that molecule becomes dipole, polarized due to that electric field. So then what is that new dipole that we call P2? That is really, that is happened because of this electric field E due to this one, times we call it polarizability. So alpha is called polarizability. That means that this electric field due to this one polarized that second molecule. So that alpha is called polarizability of that molecule. Now you have P2, it wasn't dipole before, it became a dipole due to this electric field. So then we know P2, this one. So then what is my energy? You have this P2 times that electric field. Remember, your potential energy is given by delta U, or given by minus P dot E. So what is that? Now P means P2, right? So P2 is given by alpha times E, right? Times E. E already we have this one. So if you take this one, I will just write E. That means really alpha E squared, right? So just take the square of that E squared, and you get what you get here. Please write that one. So you can see this R cube, if you take square, this becomes R6, right? So other terms you can easily calculate. You know how to take the square of two vectors, right? This is, suppose this is A minus B. A minus B, then you have to multiply by A minus B. What do you get? A squared, this is cancelled, plus minus, so this is plus 1. Sorry, this is. So then you get plus B squared. So if you do that one, you get this equation. Anyway, it doesn't matter that one. Everybody comfortable? Where you got R6? That's E6, right? So E has this R3, you get R6. So this van der Waals force has the dependence of R6. So if you have these two dipoles, so please remember this important thing. The potential energy for two dipoles given like, we have potential energy, right? Is given by something divided by R to the power 6. This is the important thing. So you know how to prove them, right?
Is that the alpha the polarizability tensor, or is this kind of similar?
So for van der Waals forces, pretty much this one. Then there are some other potentials, something called the Lennard-Jones potential. So they have some different. So, but still these are the attractive forces. So we are not talking about the repulsive forces. Okay, so that means in general you can put your potential as, so this is my attractive term, right? So this is my repulsive term. So this can be anything, right? If I take electrostatic, what is M? Electrostatic, M was 1, right? 1 over R. So if you take van der Waals, it is more like 6. Right? So like that you can, this in general you can write your total potential or the potential energy as something like minus A over Rm, so this is the attractive term, plus B over Rn. So why do we have this one? If you okay. Should be something like yeah. So if you bring these atoms or even these dipoles, right? When you bring together, you will see initially you have attractive things. So when they get closer, you have the repulsive force because of the Pauli exclusion principle, right? So this one can be negative A over Rm. This is plus B over Rn. Typically this n can be 12 or anything. So but this m depending on your force, right? If it is ionic force, this m is 1, right? A over R. So if it is van der Waals, this is basically, we showed it is 6. Something like this. In general you can write like that. If you do this computational physics, you have to first find what your attractive and repulsive forces should be, right? So that's something you have to decide. So this is what we discussed before, attractive and repulsive. Oh, then last thing I want to talk about the hydrogen bonding. Another very weak bonds, then we are finishing here. So where do we get the hydrogen bonds? So this happens especially when hydrogen atom is involved in a compound, because hydrogen has only one electron, so they can be easily bonded to another atom covalently, right? Because like even methane, they made covalent bonds with carbon, right? Like that. So even if you have other things, like even if you have something like that, still hydrogen can make bonds, covalent bonds, right? But because of that ability to make that covalent bonds, if you have any molecule with hydrogen with another atom that has higher electronegativity, things like maybe oxygen, fluorine, things like that. So then, because of that electronegativity, this hydrogen, because electronegativity means that attracts more electrons, right? So then this hydrogen becomes slightly positively charged. Suppose this is water molecule, that means you have oxygen. Oxygen is a highly electronegative atom, right? Fluorine is one of the highest electronegative element. So because of this electronegativity, that takes more negative charges. So that means this hydrogen becomes more positively charged. So now if I put these molecules together, because of this positive charge from the hydrogen, so then I have this is negative one, I say oxygen. If I have oxygen here with negative, they will make bond, right? So these are called the hydrogen bonds. See, because of this electronegativity, this hydrogen became slightly positive charge, then this became slightly negatively charged. When you put this together, if now I have two water molecules, right? They become bonded, so that's called the hydrogen bonding. So this is the last thing I want to talk. That means if I have many water molecules, if I take this one, so you can see this is negative, this hydrogen is positive, right? They make bond here. So if you take another oxygen here, this is slightly negative, this hydrogen is slightly positive, they make another hydrogen. You can see these dotted lines are hydrogen bonds. So you can see now it can form a crystal. So this is exactly how the ice is formed, right? If you take ice, you have high water molecules, they make these bonds, but you can see they are not highly crystalline, right? So this is basically how hydrogen bonds are. Not just water, there are many organic molecules, they make hydrogen bonds. These are also pretty, not highly strong bonds. These are also water, weak bonds. Okay, so you can think about some of these dependence of your bonds. You can see covalent bonds, mostly it can be one or actually it can be different, but van der Waals you can see they can be -6, right, 1 over 6. So that's some other bonds you can have. So sometimes you can have even iron dipole and things like that. This is some basic nature. Then also if you look at the properties of this bonding, ionic bonds, like I said, they are making mostly non-conducting, good ionic conductors, right? So they are very hard and brittle but non-conducting. If you take van der Waals, actually these are these, if you take these inert gases, when you cool it down, they make these crystals of, say, argon crystals. These are ionic crystals. Even if you take like these graphene layers, right? Nowadays, two-dimensional materials are very, I think, exciting, right? So between two layers, they always make van der Waals forces because they kind of polarize each layers, so they have van der Waals interaction. Metallic bonds, they are the best conductors, right? If you take gold or anything, so they are also highly ductile and malleable. So if you take van der Waals, so they are usually very strong and non-conducting, except like graphite is a good conductor, right? You cannot really generalize that one. So hydrogen bonds mostly non-conducting, like water, ice kind of thing. So they also have low melting points. Just some general description of these bonds. Yeah.
So like do you know which electrons are responsible for the van der Waals forces?
Yeah.
Is that the top electron that does the conducting, or?
No, I think what happens is if you take the, like even graphene in one layer, right? So graphene is not this one. If I take, this is one. Yeah, let's take this way. Suppose this is one layer, this is another layer. If you take this layer, on this layer electrons are moving strongly because these are mostly covalently bonded. So if I take carbon-carbon in graphene, these are all covalently bonded electrons. They can move very fast, but these electrons are there. But if you take this one and this one, so they induce some dipoles because of these electrons, right? So then they will make, between that they will make the van der Waals bonding. So on a given plane, covalent bonds, they are highly conducting. Between the layers, they are covalent. Sorry, the van der Waals. Okay, so I'm going to stop here. Any questions? You can start from. Do that. Okay. Actually, everything I discussed so far, actually, I assume you guys to know from your high school or undergraduate chemistry class, right? So I just wanted to remind you. So today actually we are going to really start the electronic structures like that. So today we're mostly going to talk about crystal structures, right? So there are so many different kind of crystals. When you talk about crystals, I think people really get confused. They sometimes consider lattice as a crystal. So that's why you have to be very clear. Crystal means you have something called space lattice. Lattice is nothing but just a geometrical entity. It's something to think about. But then we are going to decorate that lattice with some, we call the motif or basis. This can be one atom or it can be hundreds of atoms. If you take a polymer, so that basis can be large number of atoms. When you put these two together, we call that the crystal. So you have a lattice, then you have a motif, you decorate the lattice with the motif, then you get the crystal. So don't get confused with this. So that means your crystal means lattice plus motif. So motif is can be one atom or group of atoms. So lattice is the geometrical entity that has we call some periodicity. Periodicity means you can move from one place to another place and see the same environment, right? So we call that the translational symmetry. Motif is your basis that you are going to decorate with. And in real terms, you can say lattice means how you repeat or translate from one point to another one. Motif is what you are going to repeat, right? So that's basically lattice and motif. When you put these two together, you get the crystal. But still, crystal has that translational symmetry that the lattice used to have. So, translational periodicity is the important thing. Translation means if you move from one point to another point, you should see the same environment. Like if I, from here, if I see, say, 4 people around me, if I go to this place, I should see the same 4 people around me. If I go here, I should see the same 4 people around me. That's the translation symmetry. So we'll do a lot of examples to get the idea. So let's take this one. So these are just 4 points or 5 points here, right? So this is a one-dimensional situation. So typically lattice is infinite, right? If you think in terms of number of atoms, that's it's going from negative infinity to positive infinity. So these are, what are these? These are just lattices. These are lattice points. You have, we call the lattice constant, we call A. So now what I'm going to do is I'm going to put some motif or the basis onto this lattice place. But that thing you should consider exactly same way you have to put that one. Another important thing is that motif for the basis you don't have to exactly put on the lattice point. You can put even somewhere here or here, but if you put it here, every lattice point you have to put the same point. So sometimes people only think you can only associate with the exactly the lattice point. So now let's think about some motif. So this is my motif. That has, think about like 2 atoms kind of thing, right? So actually, this is not exactly one dimensional, right? This has 2-dimensional nature, right? Forget about that. One dimension means only this way. If I want to put something like this in one dimension, how do you do that? The one dimension means there's no any other dimension, right? That means it can be only something like this, okay? That's something. But just forget about that one. I just say this is my motif. Now can you make the crystal? You can, right? For each lattice point I have to put this motif like that. So you can put either at the center here, or you can look at the corner, whatever. If you do, everywhere you have to do the same way. If you do that one, what you get? So, if I add these two, that's the lattice, this is the motif. If I add what you get, I get a crystal. So, what is my crystal then? That's a crystal. So, if you look at this one, so this is why, if I didn't tell any of these, if I tell this is my crystal, and if I ask you to identify the lattice, how do you do that? So sometimes if you have no idea about the lattice, you might say these are lattice points, right? But it's not, right? Suppose if this is a lattice point, so what you have to the right? Something down. If this is the lattice point, this is up, it's not the same, right? So that means what are the lattice points? Every other point, right? If I have this one, I have something to the down. Here I have something down. So that means these are the lattice points that we knew, right? These are the lattice points. This is why sometimes if I give you the crystal, it's not very trivial to find the lattice. You have to really identify each lattice point very clearly. Now in this case, if this is the crystal, your lattice points are this one, this one, this one, this one, like that. Or other way, this one, this one. Please remember that one. That means your lattice constant is this one, not this one. This is not the lattice point, right? Lattice points mean each point should have the same environment. These are some tricky points people miss. So now look at this one again. If I take, so this is my lattice. Now I am putting my motif as I don't know. So now if I connect like this, so if I give like this again, you can tell me what my lattice points they can be. These are lattice points, right? Because if I take this one, to the left I have downward, to the left and right I should have downward. So that means if I go here, this can say downward, right? If I go here, this one we have downward. So those are the lattice points. Or even this is fine, right? This one and this, this one and this one. If I go here, I have 2 points upward. If I go here, pin it upward, right? So that means, yeah, this is fine. So you have 2 upward. So that means these are, each one is, every other point is a lattice point. Is that clear for everybody how you figure out the lattice point? So even if I have like this is not my lattice constant. What's the lattice constant? Yeah, so this, you can have 1D, 2D or 3D. So for example in this case, so you can see this is real one-dimensional case. That means my motif is this one. Okay. So these are the lattice points. If I put my motif here, so these are the, this is the lattice, right? So now lattice points, these are our lattice points, right? Because if you go here, you have to the left and right, you have the same. So this is one-dimensional one. So when you talk about lattices, not for the crystal, lattice, we can define something called the unit cell. This is also a very important concept. Unit cell means the smallest cell. In this case, it is this one, right? So here, that can be translated to create the lattice. The smallest cell, actually it's not very clear, we'll do in the 2-dimensional and 3-dimensional case. The smallest possible unit that can be translated to make the cell, because sometimes that there are many ways of finding that unit cell. So, but we like to have the smallest unit cell that we call the primitive cell. but sometimes it doesn't have to be the same smallest one. So then we call it the conventional cell. Two things everybody has to remember very carefully. The primitive unit cell is the smallest unit cell that can be translated to create the lattice. Or you can have even a little bit larger one. It's not the smallest one. They are conventional unit cells. We'll talk about that one in some detail in detail. So you can see this one definitely is the unit cell, right? If I move from here to here, you can get the next point and so on. So that's the unit cell. Is that clear for everyone? So let's do some clear example, then you get the idea. Like I said, these don't have to be exactly at the center. You can put this motif, if I put somewhere here, exactly like that. Right? So then again you can see, you can translate. The unit cell is for the lattice, not for the crystal. Right? So this is another way. Most of the time we are putting atoms here, right? Because strictly speaking, this is not one dimensional, right? This has some dimension this way, that's why it's 2D motif, 1D lattice. So, okay, so there's another concept everybody should remember, something called the sublattice. So that means if I take this lattice here, so this is the total lattice. So but I can separate this one to the one like this red ones. So these are, we call one sublattice, and these blue ones are another sublattice. So that means this is the lattice consisting of these two sublattices. So now if I have some motif attaching to this one, so this is my motif, right? So this green and blue one like this. So this is, we call the crystal. So you can find what is the lattice points for this one, right? These are actually lattice points, right? If you take this one, you can see from the both sides you have upward green ones. But you can always think about this one having one subcrystal with this green one and one with this yellow one. These are subcrystals, so by adding these two you get the total crystal. Sometimes you will see this in literature, something called the sublattices and subcrystals. So this is nothing but, typically we call this a super crystal. So this is like a subcrystals, this is like a supercrystal. There are different ways to identify that one. These are some concepts people don't see very often. So here is another two-dimensional lattice. It's just a lattice, right? How do you create the crystal? I just add this motif. If I add, so that means I have to add to each point, then I get the crystal, right? That's pretty straightforward. So this is my crystal. So in this case, you can think about spreading in both directions, X and Y direction. So this is a crystal, right? So if I show this one, you can immediately tell me what is the lattice, right? So these are definitely lattice points because each point you have the same environment. So let me ask some questions, then you will tell me these are really lattices or not. So let's look at this one. This crystal structure, if I give you, can you tell me what is the lattice or the motif? So these can be lattice points, right? Then the motif should be this whole thing, right? All four atoms should be your motif. Yeah.
Can we consider like diagonal also?
There are different ways of doing that one, but in this case, you can easily, you can think about, but you have to make sure like if you take these, right, so you have all 4 around this one, but if you come here, it's not the same, right? You have to be careful. So that's why if I give you this crystal structure, actually this is your lattice and basis. Okay? So you can see these points, right? 1, 2, 3, 4. These are the lattice points. So but each lattice point I am going to attach this motif here. You can see if I put this one, the red one, these 2, then if I can come here again, I can put red one. You can see that one. So that's why if I immediately give the crystal structure, it takes little time to think what is the lattice and what is the motif, right? Important thing is at the lattice point, everywhere you should see the same environment. Suppose these are my lattice points, right? If I can come here, you can see all 4 direction I see blue one, right? Don't worry about the corner one because this is going to infinity, right? So you don't have to worry about that. Is that clear? So now when you have this lattice and crystal, so I said you can define this primitive unit cells or conventional unit cells. So yeah.
So like the basis is just like the most fundamental structure that makes up the entire structure.
Yeah.
So like if you had graphene, then the unit cell would be like.
Yeah. The next one I'm going to talk about the graphene. I'll ask, see how many people can guess what is the lattice point for graphene.
Sorry, I was just excited. All this is
Yeah.
like.
Right. So let me. Next slide is about that one. So now when we have this kind of lattices, so we define. So like I said, you can move from one lattice point to any lattice point using, in the 3-dimensional case, we call this a 3 primitive vectors. So that means so suppose this is my starting point, I can go from here to here by adding some combination of this A1, A2, A3. So any point I should be translate using this A1, A2 and A3. We call these are primitive vectors. So the way we do is for any point here, R and M, and this is the important thing, for any place, any point, if I take this one R and M, O, I have to write in terms of this A1, A2 and A3 using some N times A1 plus M times A2 plus N times A3. This N, M and O. So this N, M and O, they have to be integers. That's the important thing. You cannot have half. So that means this can have 1, 2, 3 like that. You cannot have half this one. So how do I get from here to here? What is N? N is 1, right? What is M and O? Zeros, right? To get to this point. How about to get to this point?
N is 0, M is
N is 1, O is 0, right? If I want to get from here to here,
then N is 1, M is 1.
1, exactly. So if I want to get to this point, M is 2, right? Like that. So any point I can do by the NMN, but they all have to be integers. That's how you pick your A1, A2, A3. Can I have N1 like this vector? If I pick A1 as this vector, then this point will be half of that A1, right? The half is not the integer. So that means they don't become primitive vectors. So that's the important thing. This NMN, NMO have to be integers. Yeah, let me write this one. This basis vectors A1, A2, 3. This M, N, O have to be integers. Is that clear for everybody? So that's the important thing. So let me show you some of the primitive vectors. So these are called the basis vectors. So look at at this some two-dimensional cases. If you take, so your A1, A2, you can define like this, right? That's fine. So you can get to any point. So I want to go here, this is 2 times A1, right? So any point I can get like this. Even here I can do, if I want to get this one, A1 prime 2 times. So any point I can get from this vector. So actually these are this unit cells. So, but it's different, right? But they all should have the same area in this case. Okay, these are primitive unit cells. Primitive unit cells means you can only have your lattice point at the corners. So total, actually, if you count total number of lattice points in that square is 1. How do you know it is 1? If you take this lattice point, actually it's shared by 1, 2, 3, 4 closest ones, right? That means each lattice is only 1/4 of that point. If you go here, that is also 1/4. If you go here, that is also 1, 2, 3, 4, right? So that means you have really one lattice point means actually only 1/4. But you have how many of them? 4, right? 1, 2, 3, 4. That means you have really, what's the total number of lattice points? In that square you have only one lattice point. So primitive unit cell means you have only one lattice point. So if you can't come here, is this one primitive unit vector? No, right? So this is half of this one. So this is not a primitive cell. You can see that the area is different now. Right? But if you have primitive cells, they should have same area. If you take 1, 2, 3, these are all primitive unit cells which have equal areas, but not the fourth one, because that has something not at the corner, right? So they have something in the middle. So it's not like one cell. So you same thing for three-dimensional case. You have A1, A2, A3. So this is your unit cell, right? You can translate this way. Again, if you take this one, if I show this one, you can immediately tell me what is the lattice and basis, right? These are the center point can be the lattice points. Then your basis could be 2 atom basis, right? So that's this is has basis with 2 atoms. Okay, so let me ask this question, then you get the idea. Okay, this is basically I'm summarizing. Please read this one. Yeah. Okay, let's look at this one. Okay, this is what you're asking. So can you tell me the lattice points of this one? Are these lattice points? Let's look at this point. If I think about this one, what do you have to the right of this one? This one. If I can come here, is that same? No, right? So that means these are not lattice points. So, but you can think about every other point. If I take this one, this one, this one, take these ones. Let me show this one here. It's easy to see. Yeah, this is what I was trying to say, right? If I take every point, so you can see this one is different from this one, right? That means these are not the lattice points. Is that clear for everybody? Because if these are lattice points, they should all have the same environment, right? But if this one you have one to the right, but here nothing to the right, right? That means these cannot be lattice points. So this is, just think about this one. This one's in, this one. Take these points. This one in, the same carbon, right? But if I take this one as my lattice points, so they are fine, right? If you take this one, you have one to the right, one to the right, one to the right, one to the right. And they are equivalent, right? These can be lattice points. Exactly. You can see how you can pick your lattice points. So then unit cell is something that cell that you can translate to make the crystal, right? These can be your unit cells, but not primitive unit cell. See, if I take this one, I can translate like that to make the crystal. So even this one, if I take this one, if I can translate from here to fill this one, you can make the thing. But these are not lattice points, right? So please remember, these are lattice points, right? Okay, for everybody. So yeah, so this is basically unit cell. So this has 2 atom bases, right? So you can have 2 atoms. So actually there are more ways of finding unit cells. So if I do the same thing, here is another way of drawing that graphene. So you can see this is also unit cell, right? I can move this one to make the unit cell means some unit you just translate to make your crystal, right? So this can be a unit cell, right? So here I can move this one. So then also, how about this one? That is also unit cell, right? So there are more ways of finding unit cell. Now if you take this unit cell, how many atoms are there? You have 2 atoms. If you take this one, how many atoms are there? You should have the same number, right? But if you take this one, you can say it is shared by how many atoms? 3 atoms. That means, this means actually 1/3 of 1, right? So that means you have 1/3 of that. So but how many of them you have? 6. That means 1/3 of 6 means 2. Still have 2 atoms bases. So you can see 2 atoms. If I take this one, even here you have 2 atoms. So they both are unit cells. You have to be careful how you count this thing. Here actually it shows it nicely, right? So this is only 1/3 of this one because this one is shared by this one, and this one. So that means it has only 1/3 for itself. Okay, so now let's talk about these unit cells and some, yeah. So like I said, unit cell is easy thing, right? The smallest unit you can translate to make the crystal. So here, this is the smallest unit, right? So actually, yeah. So even half of that can be a unit cell because if you make twice that translation, you get to that point, right? But usually we don't consider that as a unit cell, smallest the unit. So this is basically unit cell, right? So then you can write this the whole thing in terms of your this A1, A2, A3. Then these unit cells have these 6 parameters everybody should remember. So that is how we define these different crystal structures. So there are these 14 Bravais lattices. These are A, B, C. So this is the most important thing to remember for anybody. If you take this unit cell, you have A, B, C, then these angles alpha, beta, gamma. So depending on this one, like is all ABCs are the same and alpha, beta, gamma are the same, we call these acubic structures. Then if one of them is different, we call this a tetragonal. If all 3 are different, still all angles are 90, we call this a orthorhombic. And so then we have sometimes this alpha, beta, gamma are not 90 degrees. Then we have different, like going from least symmetric is we call the triclinic, then coming to monoclinic and hexagonal, things like that. This all depends on this A, B, C and alpha, beta, gamma. So most symmetric thing is all ABCs are same alpha, beta, gamma 90 degrees, right? You can see typically we define this A, B, C. Then alpha is defined as your like alpha is a cyclic, right? Alpha, beta, gamma. Alpha means it's between Y and C. Beta means it's between X and C. Gamma means it's between X and Y. It's a like the cyclic thing. You can see here. So this is X, Y, Z. Typically we measure in the direction of X. That is A. The lattice parameter. In the direction of Y, we measure B. In the direction of C, we measure C, right? You can see X direction is A, Y direction is B, C direction is C. So then between X and Y, so that is your gamma, right? X and Y, so that is X and Y, that's a alpha, beta, gamma. So if you take between Y and C, so that is the second one, right? Alpha, beta, this should be beta. Y and C, so that is Y and C, sorry, yeah, Y and C should be alpha. Then X and C, that's the first and third, that should be beta, right? You can get that relationship? X, Y, C, now with X and Y, it should be gamma, Y and Z, it should be alpha, X and C, it should be beta. You can make your way of remembering that one, right? So that's how these angles are. This is how we categorize all the crystal structures. Actually, if you look at these crystals, all the systems you can actually group into these 7 structures. Then even in the 7 you can have kind of different symmetries. All together you can have only 14 lattices. We call they are Bravais lattices. So 14 Bravais lattices in 7 crystal systems. So this all depend on this symmetry operator. That I'm going to talk about in the next class. Symmetry operators, they have 2 symmetry operators. One we call the space symmetry. Other one is the point group symmetry. So there are actually 230 the space symmetry of groups, and there are 32 point group. Point group means something happening about a point, rotation or doing anything about a point. We'll talk about that one later. But right now, please remember, there are 7 types of systems having 14 different these lattice types. So, because if you take like, if I tell you like copper, what is the crystal structure? So if you remember, copper is basically a cubic, but that also has something called the face-centered cubic, right? Like that. If I ask you, what is diamond? So diamond is actually still.
Is it tetrahedron?
No, diamond also this cubic FCC, but they have 2 interpenetrating.
Oh, I'm talking about
Yeah, like
the bonding.
Yeah, so we'll go through all these systems. So these 7 crystal systems, like I said, going from cubic, that is the most symmetric. That means all ABCs are equal, all angles are 90 degrees. That's easy, right? So then if you have one little less symmetry, all AB are same but C is slightly different, we call it a tetragonal. All ABCs are different, we call it orthorhombic. So then if you go down the list, you have hexagonal, that's the interesting one. This one angle is 120 degrees, you can see here. If you have this one becomes like 120, all other angles are 90 degrees. That's a hexagonal structure, but only one is different. So then monoclinic is all this unequal, so only 290 degrees, this is not any defined angle. So this is the least symmetry, that means none of them is equal or none of them is 90 degrees. So that's very hard thing to work with. So there's also this trigonal, there's another word for this one, this is the same thing we call the rhombohedral. Please remember that one, trigonal and trigonal is same as rhombohedral. So each one of them have this, if I take cubic, they have, remember what is P? That's a primitive, remember? Lattice points are only at the corner, that means what is the total number of lattice points? Only 1, right? Because each one is shared by 8 atoms, 1 8. So you have 8 times 1 8, it becomes 1. Here, you have additional 1 here, that means you have 1 from there, and here you have 2 of them. If you can come here, you can calculate, I'll show you how to do that one. Typically we write this symbol, P means primitive, that means only at the edges of your cube. I means interstitial, like at the center you have 1 atom. F means at the surface of each, like if I take this one, so you have all at the corners, then also at the center of each face you have, that's the face center. But sometimes you have not at every face, only maybe these 2 faces, or these 2 faces, or these 2 faces. That's why we have ABC. ABC means you have only, here it is, only these 2 faces. Here, I means in the center, P means only at the corners, F means at every face, right? All 6 faces. B means not here, this is these 2 faces, right? B means only between these faces. C means between these 2 faces. So only 2 opposing faces you have at them. F means all 6 have. So we'll start from here. Please read these things. You can see 7 types, but each one can have different symmetries. So altogether you can have 14. That's all. You can have any crystal you tell me, I can put it in one of these categories. So we'll talk about all this in the next class. Okay, so it's almost time.
Will like any of the crystals only be one of them, or can it
No,
be like
if
multiple?
you give me any crystal structure, I can include it into one of these.
Okay.
Yeah, you cannot find any other.
Oh no, I was talking about like a multiple of them.
Yeah, you cannot find anything because at the end you have to find a unit cell for that one, right? That unit cell should belong to one of